cosmic blowtorches, relativistic jets from stars and galaxies. So, Roger, the floor is yours.
Thank you very much, Mark, and everyone else. It's a great pleasure to be back here, and I'm assuming Mark and so on will monitor questions as appropriate. Let me firstly try and share my screen.
Yeah, we can see it.
You can see it, and I'll now go to presenter view. Perfect. Is that still okay for a...
Yes.
Okay, and all right. This is going to be the second lecture, I guess, in this series of 5, and I've chosen as a topic cosmic jets, and as a title cosmic blowtorches, for I think a reason that will become apparent, I won't spell out. It relates to the first lecture that I gave, which was much more centered on the black holes. In this one, I'm going to say much less about the black holes and much more about the implications centered, as I say, on these jets, which I introduced particularly in the context of the nearby galaxy M87. And I'm going to tell you a bit of a story. It's a very broad, untidy story that I'll tell you. And I know Belgians love detective stories because they've originated, or many of them. And this is one that hasn't yet got, we haven't yet turned to the final pages. And so there are many unanswered questions, but I do have a sense that for reasons associated with upcoming facilities and telescopes, we're going to transition in fairly short order on a very broad front to a much more consolidated understanding as what is happening in these remarkable and ubiquitous objects. But we're not there yet, and I'm going to present what I think is often rather irritating for physicists when they hear astronomy talks, which is a lot of phenomenology. I've tried to simplify it to the point of embarrassing the astronomers, but I can't help it being a rather untidy description of lots of complicated phenomena that have been very well documented, but not terribly well rationalized. And I hope, though, that I'll be able to ask some questions and provide some direction towards where I think the field is going. So I've listed here some of my collaborators. Again,
So we cannot hear you anymore. Roger?
Roger, we lost your sound.
We are losing you. Oops. So I guess we try to get back to Roger. I think he was disconnected somehow.
Yeah.
Yeah, I cannot see him even in the list of participants.
Yeah, he'll probably reconnect. He had some troubles.
We should maybe send him a mail. I hope he realizes it.
Can you hear me?
Now, yes. Yeah, we lost you.
Can you hear me?
Now we can hear you, but yes.
Hello?
Yes. Can you hear me?
I don't know why it dropped. Our internet was actually stable. Yes, can you hear me?
Yes,
Yes.
we can.
Yeah, we first lost your voice and then we lost.
Okay, so how far had I got before I dropped? Okay, sorry?
You finished the introduction about we and detectives and the messy story about phenomenology.
Okay,
and
all right. Let's move on to the next slide then. I may have missed some of this and I apologize. Anyway, so I started, I'm just going to acknowledge a few of the many people who are responsible for
your slides are not
where
up.
we are today.
Yeah, we don't see the slides.
And just here, if I can move. Sorry?
We do not see the slides, so you have to.
Do not see the slides, so let me share those again. Excellent.
Yes.
So I want to share screen. Share. Whoops. No. I just screwed up. Share screen. Stop share. I want to share screen again. Share. Now, can you see them?
Well, it's telling us that we will see them. I think you have to. Okay, now we see them. Yeah, now we see them.
Now you see them. Okay.
Yeah.
It's clear that somewhere along the line there is a bandwidth problem, but we're doing okay using another computer at home, so I'm not quite sure where it is. Anyway, let's continue. So I said here some of the people who were pioneers of this business. I'll just say a few words about them. I don't want to linger on this. Top left-hand corner is Heber Curtis, who found the first jet just over 103 years ago, using the Lick telescope. Here's Grote Raber, who is an amateur astronomer in Wheaton, Ohio, who built his own radio telescopes in his own backyard and sort of more or less grew the field and found some of the sources we'll talk about. Here's Walter Bader, who showed that these jets associated with massive black holes, first indication that the radio sources were in fact external galaxies. Here's a sort of group photo taken at Manchester University about 1950. 3 people I'll identify. Cyril Hazard will come up, Jennison and Das Gupta here. And they'll come up in a subsequent slide here. And then I just sort of gave up at this point because there's so many pictures I could have put on here. And so I just picked 3 of my friends and colleagues, Martin Schmidt, who found quasars, Marshall Cohen, who was one of the pioneers of very long baseline interferometry, which you saw last lecture in the case of the Event Horizon Telescope, Tony Reedhead, who pushed these techniques in terms of imaging and also to shorter wavelengths, to millimeter wavelengths, along with many other people. And then my current colleague at Stanford, Peter Michelson, who led the Gammaray telescope, Fermi Gamma Ray Space Telescope, excuse me, and that has told us also a lot about jets. So let me move on to the next slide. Okay, so this is a slide I took from last time, which is M87, and I'm not going to go through this one more time. It's just to remind you that there is this galaxy which Event Horizon Telescope imaged, and it has this jet. And a region smaller than the solar system is able to have a major environmental impact on the gas surrounding this elliptical galaxy. And these types of jets always happen with elliptical galaxies, a pertinent clue in the detective story. And this is the surrounding gas surrounding the galaxy in the cluster of galaxies, and it's heated by this machine that's even smaller in relative terms than the nucleus inside an atom, which of course can pack a lot of heat too. And so it's a really remarkable thing, something small. I'll say it again, something small in the solar system illuminates something much, much larger than the galaxy. And it does this through these channels, beams, jets, exhausts. I like the metaphor of an exhaust. I'll come to that again. But the jet is the most common word to use, which transport power mainly, but also momentum, energy, magnetic flux, and much other good stuff, maybe cosmic rays as well, probably, out into the intergalactic medium. And we see them on different scales here, and we see the structure, and I can't do justice to the observation. We also see them, of course, throughout the electromagnetic spectrum. So let me turn to another one of these sources, and this is one of the prototypical sources. It's Cygnus A. It's one of the ones that was found by Grote Reber. In fact, it goes overheaded in Illinois, and this is what he found. This was a map he made of the sky, and in fact, you can just about find Cygnus A. They did this in the 1940s. Actually, he was still doing it, he was more or less doing it in late 1930s, but certainly early 1940s. And it was really the birth of radio astronomy as an astronomy. And Jennison and Dasgupta, using an early application of interferometry, that's using two telescopes basically, it's a real tour de force at the time in the 1950s. They were able to show that this source Cygnus A is actually not just a single source, but it's two sources. And then a little bit later, Walter Bader, who I showed you, and Minkowski showed that they were on these two sources, although it didn't happen in this order, but very quickly it became clear that these two sources straddled a nearby a galaxy at some considerable distance, and therefore these sources were immensely powerful. We now know that it's an elliptical galaxy. It's a high power. This is called a radio galaxy. It's much more powerful. It's about 2 orders of magnitude more powerful, I would say, 2 or 3 orders of magnitude powerful than M87. And it's the prototypical powerful radio source, extragalactic radio source. So this is what it looks like today. This is the nucleus of the galaxy. Here we see these two jets quite clearly. They're almost these ones are almost perpendicular to the line of sight. They go off in anti-parallel directions, and they have so much power that they carry out into the intergalactic medium that they can illuminate these what are called hotspots in these giant lobes of radio emission. And so these two lobes of radio emission are these two blobs that were found by Jennison and Dasgupta in the 1950s. And if we look not just at radio wavelengths, which is the red color here, but we also look at X-ray wavelengths, which is the blue color, and we look at optical wavelengths, which is the sort of white. This is the stars there and all the galaxies that are surrounding it, and this is the primary galaxy. You see rather clearly how these jets are squirting right outside the galaxy into the intergalactic medium. And some of the jets that we observe from galaxies are 10 times larger in linear size than the ones we see here. Furthermore, as was clear from M87, if we trace these jets right down into the center of the galaxy, and this is 1 milliarc second here, this scale here, 10 to the minus 8 radians, thereabouts, and on scales 10 to the minus 9 radians, nanoradians if we prefer, we're seeing jets still being present. And we believe that these are made from much smaller structures on the microarc second scale, less than microarc second scale, around the black hole in the galaxy associated with Cygnus A. So here's at my third prototypical example, which is 3C273. It's the first quasar. And the two gentlemen I showed you pictures of, Cyril Hazard, he was a radio astronomer, also, and he used the technique of interferometry actually in Australia, and was able to make an identification, say where on the sky 3C273 was. And then Martin Schmidt, who was an optical astronomer, oversimplifying a more complicated story, was really the first person to see that the funny spectrum that it showed was in fact a not so atypical spectrum, but one at an enormous redshift. So this galaxy was receding at enormous speed from us. It was very distant in the universe, and therefore it was correspondingly powerful. This is the first quasar, and we know essentially millions of them now, and some of them are even more powerful and even more strange, but it shows many of the features that we need. This just shows you the shift of the spectral lines. This shows you it's inside a galaxy. This is a Hubble image showing it's inside a galaxy. It has a jet, this case, just shown here. This is an early image. This was known from the start. This was actually Cyril Hazard had realized that there was a jet there. Well, he didn't call it that, but he did. And then we observed this jet at X-ray radio and optical wavelengths. And you can see features on it. And I'm not going to go through the detailed anatomy of this, although this is obviously very important and interesting for interpreting what we see. Let me just say that one of the most important things about this jet is that in this case, unlike in Cygnus A, where the jet is almost perpendicular to the line of sight, and in M87, whereas I think I mentioned it's about 20 degrees to the line of sight, this jet is within a few degrees of the line of sight. In fact, it's almost pointed towards us. And that means it's what's called, we call that a blazar when we get a jet that is pointed towards us. And as I mentioned last time, these jets are made as outflows with relativistic speeds. And so when we get something radiating and moving towards us with relativistic speed, firstly, it is very bright. It is going to be a lot of aberration associated with it, and the emission is very bright. So that means it will be very prominent in our lists of these sources. Indeed, that is the case. And secondly, if it just comes at a slight angle to the line of sight, there are kinematic effects known as now as superluminal expansion, and you can see this rather graphically in an old paper by Reedhead et al. That shows the feature here in the jet that's moving apparently across the sky 30 light years in basically 3 years. And so that means it's moving at roughly 10 times the speed of light. And so it's not unusual for sources like these so-called blazars that are pointed with the jets pointed towards us to be very bright and to show superluminal expansion. And furthermore, they emit throughout the whole electromagnetic spectrum. And here's the gamma ray emission from the jet of 3C273. And this quasar shows gamma ray emission that's rapidly variable. In this case, in this example, it's variable on the timescale of a day or so. You can see rapid variations on the timescale of a day. So it's very, light crossing time, if you like, of a solar system. And if you look at one other quasar, which I will come back to, which is called 3C279, not 3C273, but 3C279, that is one that shows timescale variations on timescales of minutes, about 3 minutes in the frame of the source. So that is truly remarkable. One's looking at gamma ray emission that varies on these, in less time than it takes light to get here from the sun. So that is truly remarkable. And this is the sort of prototypical quasar, if you like. It's the first one, but it shows many of the features that we try as astrophysicists to understand. I'll say a little bit more about the clues that we've got from very long baseline interferometry. And there's a huge more I could say, but just let me try and summarize it as best I can here, what's been going on recently. And you saw some of this in M87. And here's another radio source called 3C84. Don't worry about the telephone numbers. From a telescope in space. And basically the story that is emerging is that when one looks at the images on the small scale, not on the scale of the Event Horizon Telescope, not on the scale of the black hole, but on scales from about 10 times that upwards, then one finds that the jets are collimated. They're being made more and more into linear features. You can see that rather graphically here, but you can see the same thing here. So on scales from about 10 times the gravitational radius, the size of the black hole, to about 10 million times to 1 million times the gravitational radius. And as I sort of started to suggest that last time, and we'll develop the idea a little bit more here, it's a prime candidate that this is actually caused by a hydromagnetic wind. And one of the merits that you'll see of doing this is that the hydromagnetic winds, other than other agencies that one could invoke, are don't radiate as much. If it were hot gas, for example, that were doing this, then the hot gas would radiate X-rays, and you see far more powerful X-ray sources in the nuclei of these galaxies than you do. So doing a lot of the challenge astrophysically is to explain why it's invisible. So at any rate, so what we're looking at here in these is not just the collimation, we're also looking at the fact that the emission is coming from what appears to be the surface. It looks like the surface of a cylinder. And if you're any experience with fluid mechanics, you immediately think of a boundary layer. You think of having some supersonic flow, which in this case is going to be relativistic as well, but it doesn't stop it being supersonic, and it is supersonic. And it's going to have a boundary layer, and it's going to entrain gas. Entrain gas from its surroundings. And if we allow me to conjecture that this is a hydromagnetic wind that's causing the collimation, the wind will be traveling much more slowly. It's essentially at rest with respect to the jet, and so it will entrain the gas in here. But several other things will happen. Everything is magnetized, and so the magnetic field, when it's stuck in this shear flow, is going to be stretched, and that means it's strengthened. There's also going to be a lot of dissipation associated with this, stretching these field lines. I'll explain this a little bit more in a moment, but there'll be dissipation associated with this. And for these purposes, dissipation is not just sort of heating or viscous or ohmic heating or whatever. It is going to be particle acceleration. The dissipation in this sort of environment is the acceleration of relativistic electrons, which can radiate synchrotron radiation and scatter photons through the Compton process. And this produced polarization, which is rather distinctive for this sort of emission. And it is, of course, seen in these objects. So that's some of the things we've learned from VLBI observations. And as I'm sort of, telling the detective story, giving you the evidence as it were, let's say a little bit more about these AGN jets that I sort of emphasize. There's probably a billion or so of them to look at in the sky. They've already been counted. But here are a few ones, and here are just a few images that have been made over the years. And these are more low power jets, more like M87 rather than the Cygnus A type. And this is one called NGC 6251. It was historically quite important because it was one of the first ones that showed this hierarchy of scales of the jet, like some Matryoshka doll or something, expanding out to quite large. But this is actually much larger than Cygnus A. It was probably much more powerful in the past. Here's Centaurus A, which is about 10 million light years away. It's very close by galaxy. It's a massive galaxy. This is a significant fraction of the sky you're looking at here. That's 1 degree on the sky. So the whole thing's, about 7 or 8 degrees across that you can trace it on the sky. So that's a significant fraction of the sky. It's got jets in its center and a counterjet, a massive black hole and so on. And we see this, of course, throughout the electromagnetic spectrum. So there's a black hole there. Here are ones where what happens in these low power jets typically is that there isn't enough power in the jet to fight their way supersonically through to the end of the sources. And so instead they become subsonic flows. They get decelerated to subsonic flows. They become subrelativistic. There's no relativistic beaming. And they can be swung around, as in this case. They can be precessed, as presumably happened in this case and in this case. And they can have companion stars, which can also lead to, in fact, in this case, 2 jets. And so there's lots of things that are going on, but you're basically looking at subsonic flows at this point and not relativistic ones. And I'll return to this point because I think it is an important clue. Let me just emphasize that this business of jets is not just a peculiarity of extragalactic radio sources. It is a common phenomenon in astronomy. And here's just one of each of these images here could take a lecture course, let alone a lecture. So, but let me just summarize what are the salient features. This is one, I'm not sure if I showed it last time, but this is a South African telescope called Meerkat, and it's been wonderfully successful, and it can be used for many purposes, but one of them is to count the number of sources on the sky. And as I say, it looks like there's a billion of these jet-like sources already counted, and many more, of course, that they're too faint to see. Jets aren't just associated with black holes. Here is the Crab Nebula, the most famous supernova remnant. Here's an X-ray image in blue superimposed on the optical emission line image. It was a supernova that went off in our time of 1054 AD, observed by Chinese astronomers, and it's been expanding ever since. And it's got a neutron star. There's absolutely no question. It's the most famous probably of the pulsars, the radio pulsars. It's got a 33 millisecond period. And lo and behold, it makes jets. It's not a black hole, it's a pulsar, and yet it can make these two jets. You can see them here. And other supernova remnants also, with pulsars in them, also make jets. And so it's a quite common phenomenon. It's nothing peculiar to black holes everywhere. Just to emphasize that point, here's probably the most famous protostellar star observed by the telescope ALMA, the one that was the anchor of the Event Horizon telescope. It shows, this was a very famous image that was made. It shows these rings that are made here by protoplanets in the protoplanetary disk. And this is a beautiful dynamical phenomenon. And you've got everybody's focused on this disk here, but lo and behold, it's got jets associated with it. This structure makes jets, and there's certainly not a black hole there, not a neutron star, there's a protostar. But what there is angular momentum and mass, and a source of power. And most important of all, there will be magnetic field there. That would be my contention. Here's another famous source. This is an example of dozens of X-ray binary sources. This one is called SS433. It is it was first found in the 1970s, and it is almost certainly a black hole with a binary companion. It's probably got a mass around about in the 10 to 30 solar mass range. People contest what the mass actually is, but it's probably in that range. It's surrounded by an accretion disk, and through mechanisms which are not agreed upon, that the jet and the accretion disk precess in space. And they lead to this feature here. It precesses with a time scale of 163 days, and it precesses and leaves this sort of sky writing on the sky. These are images made with a radio telescope. And this also has a supernova remnant associated with it. And recently it's been shown to be a source of TeV gamma rays, not just GeV gamma rays, but TeV gamma rays. So this is a prodigious particle accelerator as well as a producer of jets. Here's TXS 0506 plus 056. It is a PeV, not TeV, but PeV. A PeV is 1,000 TeV, 10 to the 15 electron volt neutrino source. We believe the identification of the neutrino source, and IceCube and other telescopes at the South Pole have been finding cosmogenic neutrino sources. They are in the business of trying to identify them. And this is one of the most promising associations, is of one particular source that's well studied with a blazar, an extragalactic jet that's pointed towards us. And this is the name of the source. And the identification, as I emphasize, is not totally secure, but it's certainly a highly plausible identification, and there probably are many more. We know that they're looking at a richer astronomy, because not all of the sources that they're finding can be these types of jets. And so everyone's sort of eager to find out what exactly they are. Lots of discovery space there. And then finally, here's the second most famous, if you like, gravitational radiation source, the one that was the merging neutron stars, GW 170817. I'll say a little bit more about that, nothing like as much as I should say. It was a spectacular sort of fount of discovery, and for a long while it just looked like a more or less isotropic source, and everyone told the radio astronomers to fold their tents and leave, but they kept on observing, and eventually, after about 50 days or so, they found that it too creates jets. And so this famous neutron star gravitational wave source, merger gravitational wave source, is also a producer of jets. And there are many other examples of different types of astronomical phenomena where one sees jets. So it's a very generic type of process one's looking here, not something that's highly specialized to one environment. There's what's become a cliche now, which is multi-messenger astronomy. It was actually a phrase that was coined. I was present at the coining, but I wasn't the coiner in 2000, that's 20 years ago. But sometimes it was a good phrase then, and it's now become quite popular. And it's basically the notion that you use the entire electromagnetic spectrum from the lowest frequency, longest wavelength radio waves to the highest energy gamma rays. And you look throughout the whole electromagnetic spectrum, most of which in a logarithmic sense is become accessible. And there are 70 octaves worth to play with, 10 grand pianos worth. And then you throw in the neutrinos, the gravitational waves, the cosmic rays, and so on. You've got about another 70 octaves to look at. So it's not surprising you get a much richer view than looking through the one octave accessible to a traditional optical astronomer. And you see a minute variability from blazars and quasars and so on. We see things like GW 1717, and we see TXS, this ice cube source with the PeV neutrinos and so on. And the list here gets longer and longer of all the discoveries that have been made by cross-correlating the observations of these time variable sources over all 140 octaves, if you like, of accessible astronomy observing space. So I will say just a little bit more about the gamma ray bursts, and I wish I had longer to say so much more to say, but the story has been told many times and might be familiar. Firstly, there are basically traditionally 3 types of gamma ray bursts, and they were known since the 1960s. It turns out. They're what are called the soft gamma repeaters. These are associated with neutron stars, particularly highly magnetized ones. I will talk about those in the next lecture, no more to be said now. Then there are what are called the long gamma ray bursts. They are typically have durations roughly more than about 2 seconds. So this is the longer and the short of it, if you like. And these are now mostly associated with massive star supernova explosions. There may be 1 or 2 exceptions out there and so on. This is astronomy, but basically they're associated with massive stars, end their lives, live fast, die young, millions to 100 million years, say, and they make a supernova explosion when the center cannot hold. And a subset of those supernova explosions, not all of them, maybe 1% or so, end up with the right conditions to make a black hole and a gamma ray burst. And in many respects, many of us believe that when the gamma ray burst is the sort of birth cry of a black hole in a supernova explosion. Most supernova explosions may make neutron stars. The minority that make black holes may make also gamma ray bursts. That's highly conjectural, but it's a good hypothesis to address if you're an observational astronomer. And then the third category are the short gamma ray bursts, and these are again a quite different phenomenon, where they are now, after 1708-17, associated with neutron star mergers. and they probably leave a spinning black hole, but the possibility that a short-lived neutron star might be made, you can't completely close that out. I would doubt it, frankly, but it's still a possibility, and it's an interesting one if it turns out to be the case. So we have these three types of gamma ray bursts, and the bottom two are make jets, and that's we see these. They may not always make them, but they're able to make them. And the natural conjecture is that a small scale version of the processes that we've sort of rehearsed for M87 and other massive black holes, just a small scale version, will work in this case too. So I think at this point it's probably useful to just summarize and make a list, no more than that, of the different types of jets we get. If we sort of look at those associated with stellar black holes, this is a serious oversimplification. The gamma ray bursts make them, the long ones and the short ones, with different physical identifications. The X-ray binary stars, where you've got one compact object, in particular when it's a black hole, and then this gas being given to it, donated to it by a companion regular star through a disk and a wind. And these also can make jets. They're sometimes called microquasars or galactic superluminals, just emphasizing the connection to the massive black holes. And the massive black holes, there are the radio galaxies, there are the powerful ones that can blast their way out into the intergalactic medium, and the weak ones, which are decelerated and become subsonic plumes and so on. And then there are the quasars, which are very bright throughout the electromagnetic spectrum. They radiate very efficiently, and they can be radio loud and radio quiet. And we call these extragalactic jets, when they're pointed towards us, blazars. And then we see jets associated with many other types of phenomenon, like pulsars and protostars, and there's many other things as well. So it's a quite generic process. So that is a sort of summary, if you like, of the types of objects that make jets. So last time I called my talk Nature or Nurture, and I sort of emphasized that in the context of M87, I was making a slightly radical claim that, in fact, in that case, it was nature that was calling the shots, providing the power, that it was the black hole that had been spun up rapidly by accretion, and there's about a tenth of mc squared of rotation power available for the taking using the electromagnetic field in the black holes. And this was the sort of slightly heretical or radical part, is that this may also power an ejection disk from which essentially all of the gas that is supplied is ejected before it gets to the black hole, and this requires an electromagnetic clutch. And I sort of emphasized that using advertising for BMWs, I don't own one, by the way, but here's the B and the M and the W, and in different ways. And then here's one model that I discovered on the web had a twin exhaust. So you could think that a BMW makes a twin exhaust. Those are the two jets. Now, I did emphasize last time that this, I did not believe, and I don't think any person could believe, that something like the quasars were powered just by disk power. They've got to radiate. Those disks have got to release gravitational energy. In those cases, it looks like a very strong case can be made that the gas makes it all the way down. And yes, there's probably rotation power, particularly those who make the jets. But the big optical and X-ray displays that are seen from these sources are really powered by gravitational energy in the accreting gas, which is not being ejected, not being seriously ejected. Some of it is being ejected, I think, for sure, but much of it makes it down towards the black hole, which it can fuel. And just to emphasize that this gravitational power, whichever way it comes, is much more than nuclear and atomic power. And those are sort of sideshows mostly in what's going on. So let me now raise some questions, and I've just tried to consolidate this into 3 questions, and there's really only time just to give a flavor of some ways in which these may be answered. And this will, there's I cannot do justice to all of the work that's been done, and in particular I removed all the truly impressive simulations that have been carried out, because there just isn't time to show movies and so on. But much has been learned from these simulations, as well as from sort of pure theoretical thought, and most of all, of course, from observation. So here are my 3 questions. Let's turn to the first of them. How are the jets collimated? And I ought to say, perhaps, I may have to sort of go through a little bit of magnetohydrodynamics here, and I'm thinking now about non-relativistic magnetohydrodynamics. And I like to think of this as something that appears in pop psychology manuals. Not sure how many in the audience are aficionados of these, but 2 of the phrases that appear quite often are go with the flow, or lead transport into some circumstances. And if you want to write this as a differential equation, you'll write something like this. And basically what it says is, in the language of Hannes Alfvén, magnetic field lines, think of them as magnetic field lines in the way that Michael Faraday did. They are frozen into a moving conducting fluid. So if your fluid is a good conductor, and astrophysical fluids generally are, then those field lines will just go with the flow. They will just move along with the fluid. So if there's a wind going out from an accretion disk, it will carry the magnetic field lines along with it. And the second pop psychological precept is sometimes called push-pull. And this, of course, has its expression in physics through the Maxwell stress tensor, which for a magnetic field, and also, of course, for an electric field, but it's a magnetic field that concerns us non-relativistically, is a sum of an isotropic pressure and a tension along the magnetic field. And so the net stress, if you think about it along the magnetic field, it's b squared over mu naught is the tension, and b squared over 2 mu naught is the pressure. Then the next stress along the magnetic field is a tension, which is equal to minus the energy density. And those who are mystified by dark energy and cosmological constants, where you get the same equation of state, if you like, this is a 1D. Magnetic field provides a very old-fashioned 1D expression of the pressure equal to minus the energy density. Of course, in the case of cosmology, one's looking at something that is three-dimensional in its stress, but nonetheless, it's not so mysterious if you think about it from a magnetic point of view. Now, the fact that there's tension in the magnetic field means you get waves, hydromagnetic waves. Again, I'm not going to go through all of these and many more besides. But what I would like to go through, and this is in some sense one of the theses that I think is characteristic of all of these sources, is that if you have a wind with a magnetic field associated, it's a hydromagnetic wind, is the most reasonable thing to do. And here's what's here we go. If you imagine just schematically having an accretion disk like that in Keplerian orbit about a central object, say a black hole, and we have a magnetic field line pointed out like that, and then we put some conducting gas that's going to go with the flow, you can probably easily imagine 2 things. One is that if this field line is inclined enough, in fact, it's more than 30 degrees to the vertical, for the simplest case, then this blob of gas is going to be flung out centrifugally. So there's a natural mechanism for launching winds in a cold way from an accretion disk and driving the gas out like that. Furthermore, this gas is going to have inertia, and therefore it's going to cause the field lines to bend backwards with respect to the rotating foot point of the field line, and therefore it will create toroidal magnetic field like this. And this toroidal field has a tension associated with it, has a hoop stress like the bands on a barrel, and it will provide a collimation for the jet. So that's the essential mechanism here. And one way to think about this is if we've got a current here in red, going up the center of the jet. Just is just schematic. It's, obviously simulations are much more complicated. We're going to have a return current on the walls of the jet like this. It's going to support in this region in between in the simplest case, a toroidal magnetic field, which we're going to scale as 1 over radius and cylindrical radius. And ultimately, it's going to be confined by pressure or inertia of gas. But the key thing is that the tension, the magnetic stress here scales as 1 over r squared. So by this very simple mechanism, the long straight wire, as it were, one can confine much more pressure than there is ultimately outside. And this is one of the good mechanisms for explaining how the jets can have so much pressure inside them when the pressure outside seems to be much less. And it's sort of something you can do easily with magnetic field and not so easily with just regular gas pressure. And these will obviously naturally launch, they'll carry off the angular momentum and so on. And the contention is that it's these magnetic fields that provide the collimation in these jets. Now, how do the jets accelerate? And I should say, in this case, I'm talking not about although it's an interesting question, the acceleration of the jets as a fluid changing its velocity. I'm talking about them as being particle accelerators. How do they actually accelerate? How do they accelerate charged particles? And remember that I said in the case of M87, we had a voltage there of, well, I think in that case, I sort of advertised modestly a voltage of 10 exavolts and a current of 100 petamps. In the case of a really powerful source like Cygnus A or Clichy 273, where a significant fraction of a zetavolt, 10 to the 21 volts, is the characteristic voltage, and the corresponding current is 100th of that in SI units. And if we go to the Gammaray Bursts, it's 100 times larger than that. So these are prodigious accelerators. The vacuum is almost inevitably a perfect conductor under these circumstances. But you have to ask, well, how are particles actually rapidly accelerated to radiate, particularly in the boundary layers associated with the jets? And the mechanisms that's most commonly invoked, and I think rightly so, because it's inevitable, is that when you have magnetic fields, and if you tie a knot in them, just shown schematically in this trefoil knot here, then in order for them to resolve that knot, there's got to be a reconnection of magnetic field lines across that knot there. That produces large local electric fields which accelerate particles, and this is well simulated in many different ways. I'm not going to say any more about it. There's another process, though, that I think is somewhat neglected and is probably just as important. If we imagine instead of having a trefoil, we have a slip knot here, then this slip knot, we can resolve that too. And it's a much faster process that will produce in a relativistic environment a large inductive electric field, which can also accelerate and trap a significant fraction of the zetavolt we've got available. Now, there's one thing that's generally taught and thought about these blazars. If we look at the blazars, then they typically have spectra throughout the whole electromagnetic spectrum, the multi-messenger business, from low radio frequencies up to the highest energy gamma rays. Then we see this sort of Bactrian shape, these two humps here. This is generally said that's synchrotron radiation, that's inverse Compton radiation. But there are real problems with that. And as I said, I'm going to introduce some heresies, and my heresy is that in many of these cases, particularly the variable cases, what one is looking at is this is also synchrotron radiation. And what is going on is that it's not the electrons that are being accelerated to high energy, it's the protons that are being accelerated to high energy, and those create pairs through the beta-Heitler process. And those beta-Heitler pairs lose energy dramatically and rapidly, very close to the black hole, and they're responsible for this emission. So that's the sort of one of the heretical ideas. Oh, and I should also say, and I'll come to this in the fourth lecture, these jets are, because I've talked about zetavolt, they're plausible sources of the highest energy cosmic rays. But I'm going to discuss that a bit and give an alternative answer to that question in the fourth lecture. Now, how do jets relate to their environment? And here, I think one can think about these as should think about this very schematically as like a chemical engineer, as a flow process. And so I've just oversimplified something. And these are the ingredients of all of these sort of phenomenological interpretations, if you like. If there's a black hole, although maybe it's functionally equivalent, it may or may not create a jet, and that why it does this is an interesting question. There's a disk surrounding it because gas has angular momentum. It will form a disk almost inevitably, and the disk itself may or may not radiate. If it can radiate, it will lose a lot of energy efficiently in the form of ultraviolet or X-ray radiation. It can also lose energy. If it can't do that, it will lose energy as a wind with losing mass. The wind, as I say, because you've got these magnetic fields, which can create a large lever arm, can carry off a lot of energy and especially angular momentum. The disk itself is supplied with mass and angular momentum. And the angular momentum all resides at large radius. The energy is, of course, is small radius. And understanding the different pathways here essentially distinguishes the different types of active object, both massive and stellar, black holes, massive and stellar, and other objects as well. And quasars are different from low power radio sources. And it's really what is supplied and the nature of the central object that are controlling the phenomenology, the different types of object that you see. And I won't go into this anymore. I just want to just put this on the table as a throw process. I want to say make two points though. One is that a very important radius in this business is when the characteristic escape velocity is the characteristic speed in the nucleus of a galaxy, which is the characteristic speed of the stars, which is about 300 kilometers a second. And that is called the Bondi radius, when the escape velocity or the dynamical velocity is equal to the characteristic speed of the stars. And so when the mass is dominated by the stars, not the black hole, and that's about 1,000,000 times the gravitational radius, m. And this is very important. It's probably very important for determining whether you've got a sort of low power or a high power jet. Sorry, this way, that way. But there's one other thing that I think is very important. I emphasized that these jets are made, are made by elliptical galaxies, not by spiral galaxies. And this seems to be a very permanent feature requiring a permanent explanation, not something that's happening very close to the black hole, but something happening way out here at the Bondi radius or beyond. And another heretical thought is that all of this is determined by how the gas is supplied at the largest radius. If it's supplied quasi-spherically, then it's very good at trapping magnetic field, concentrating magnetic field in this whole environment and giving you powerful jets and all the rest of it. If it's in a galaxy like our own, a disk galaxy, then maybe the magnetic field can escape, it doesn't concentrate, and maybe we don't get the powerful jets. And that indeed is consistent with the rather striking phenomenology that these powerful jets come from the black holes with where the gas is supplied essentially quasi-spherically. So let me just say one other thing. I mentioned that there were the quasars, and here's just a cartoon from long ago. Here's a black hole here. Here's an accretion disk, lots of complicated magnetic field, not the stylized ones I showed. And I said gas will be flung out. Well, it turns out there's one sees the quasars by the irradiated gas in clouds surrounding the accreting black hole and its accretion disk, and that gas moves with very high speed. And the contention is that it's not gas falling in or orbiting, it actually is gas that is being flung out in a hydromagnetic wind. And that's another way that jets can be interacting with disks and their environment. This again is a somewhat radical idea, but I think it's one that's easily testable, and the observations are becoming available to test it. So let me just summarize. I've told you a little bit, I hope, about jets. It's all been rather phenomenological. I promise that the next 3 lectures will be much more focused on physics, but there's no escape from the complicated detective story that we have here. We're looking at what looks like a generic phenomenon. How are the jets? And then I raised 3 questions. How are the jets collimated? And it could be that they're collimated right at the black hole by a clutch or a torus, as I brought up those 2 possibilities last time. Further out, the jets, I'm arguing much more strongly that there's a toroidal magnetic field in a wind that's responsible for focusing them. And ultimately, they're collimated by the pressure. It might be the pressure of an infalling star in the case of a Gammaray burst. It might be inertia of gas that's falling into a galaxy. Then there's how do the jets accelerate and radiate through boundary layers. There are many mechanisms that are, I just sort of sketched a few of them, and they could in principle be responsible for ultra high energy cosmic rays. And then finally, what is the connection between the jet and the disk? And here I think one should look at the flows of mass and of energy and angular momentum, try to understand, and this again is becoming an observation of observational investigation now, black hole, where the black hole spin is important or irrelevant, are there ejection disks and so on, and what is the relationship between disk winds and the emission lines by which astronomers recognize many of these active objects, both at stellar and massive scales. So I'm sorry this has been a rather breathless tour at the top level, as it were, of a very large field, but I hope I've given you the sense that there's a lot of physics to be done here, and indeed the tools to do it both observationally and in terms of simulation, which is teaching us a lot, are out there. And so this is an exciting time in this business. Thank you very much indeed, and do keep well.
Thank you. Thank you for this wonderful lecture. So we have time for questions. So Alex and I are trying to spot, and if there are people raising their hands, maybe you speak up.
Ronnie Cappens.
Ah, yes.
Yes, hello. Thanks
Hello.
again. Thanks for the great talk. I had one question. So you talked a few times already about this electromagnetic clutch. Can you clarify that a little bit, and in the diversity of jets that you have so eloquently described, for which type of jets do you think that thing actually matters? Does it require GR processes at all, or I understood it's just in the context of this force-free electrodynamics that it's centered, right?
Right. Okay. Yeah. I'm so glad you asked that question, because it's one of the sort of points that I just did not have time to go through, and I can only give you a little bit of an answer, as you said, because I do not understand what is possible there. I would say logically it's required if you want the black hole spin to drive away all the gas, essentially all the gas. So you've got to have you've got to engage some clutch there in an automotive sense to do that. And where I think the evidence that something like that is happening are in the low power sources, in the radio galaxies, in M87, which is where we have the best observations in some sense. And there I argue that the gas surrounding the black hole is impressively dim relative to the jets that the black hole is making. And there's more to it, but that's probably the most important argument. And so if you don't have enough gas there to confine those jets, you have to do it with magnetic fields, and that can't go on forever. You've got to confine those magnetic fields. So the contention is that the sort of what are called magnetically arrested or choked accretion flows, yes, they're really happening, but they're happening on a larger scale. And what Event Horizon Telescope is looking at is essentially a magnetosphere, a magnetically dominated region. So I would only invoke it in sources like that. I think all the evidence in, say, a quasar like 3C273 or 3C279, these are immense. These outshine their host galaxies by 100 or even 1,000. These are immensely powerful optical sources. I don't think this is ever going to be an explanation for that. And you have to invoke the dissipation, magnetic dissipation of infalling gas falling through an accretion disk, radiating from its surface, which, as you will know, is a rather complicated process. It's much more complicated than the stellar atmosphere, but nonetheless, in principle, the details are very much contentious, but the principles and black body radiation and all of that works out sort of roughly. And I would say that's right. The only other thing I would say is that when you're in the quasar business rather than the M87 business, then having all that radiation there is another mechanism for driving the winds. So, and there's been a lot of thought and work on this, is using the radiation to drive out the gas as well as using the magnetic field to fling it out centrifugally.
Okay, thanks.
Any other question? So please raise your hand or just speak up. There is a question by. So maybe you can. I cannot.
Pierre Gaspard.
Okay. Please go ahead.
Pierre Gaspard.
So thank you very much for your very beautiful lecture. I have a question, but it's not about relativistic jets. It's different. For some time, I've been wondering, it's about the kick that neutron stars get from supernova explosions. So we know that the kick is due to a Rayleigh-Taylor instability. And I'm wondering if there could be a correlation between the direction of the kick and the spin or the magnetic field of the neutron star due to parity violation by weak nuclear interaction. I wonder if this has been discussed. I think this has been discussed, and I don't know what is the current status about this question.
Well, that's a genuinely interesting question, and yes, people have thought about that, and I think that I'm perhaps not completely current on this, but as of perhaps a few years ago at least, I would say there's no question that pulsars have large kicks. They move off with speeds that can be more than 1,000 kilometers a second in some cases. So this really happens. Trying to correlate that with the shape, particularly of the supernova remnants, there are some famous supernova remnants that look like they show a rather clear bilateral symmetry. And that may reflect either an external magnetic field or the spin of the parent star. So that gives you something to correlate against, with the physical connection. And my recollection from a few years ago is that was not compelling. But there's no question that neutron stars have kick velocities. Some of them don't, but some do. And in terms of what's going on physically, I think most it's kind of complicated, but there are sort of modes that are trying to grow. There are instabilities in the infalling gas as, you know, just before the supernova explosion turns everything around. And if you have sort of random, very low L modes in that gas, then you're just dealing with one or two modes, maybe, you know, LE's 1, 2, or 3, or something like that. And it can be quite random, the disposition of the momentum density of the infalling gas with angle just before neutrinos take over and push everything out. And so it may not be related to the, you know, the symmetry properties of the parent star. It may just be some vagary associated with which mode happened to get started first in the infalling gas. So, but, you know, it's a genuinely interesting problem, and I think one where discoveries could yet happen. But I think it's a bit ambiguous observationally right now.
Okay, thank you very much.
And thank you. Yeah.
So, any other question? I cannot see any. Well, I guess then we should stop here. So let me remind you that the next lecture will be on Friday, this coming Friday, the 19th of March, at 4 o'clock Brussels time, so earlier than it was today. And that will be on fast radio burst. And with this, let's thank again Roger for this very beautiful lecture. So thank you.
Thank you very much indeed.
Bye, Roger.
Bye.